On the night of October 2, 2025, at 03:14 UTC, the Perseverance rover on Mars tilted its skycam upward and captured something that shouldn't have been there. A faint streak, a smudge against the Martian dawn, a point of light moving against the stars. The image was logged automatically, transmitted to Earth, catalogued in NASA's deep archive, and then, for reasons no one has publicly explained, it was classified as anomalous pending review. 3 days later, ESA released a photograph taken by Mars Express. Same object, same trajectory, same inexplicable silence from the agencies that saw it first. The object has a designation now, 3I Atlas. The 3I stands for Third Interstellar, the third confirmed visitor from beyond our solar system. The first was Oumuamua in 2017. The second was Borisov in 2019. Both were comets, or at least comet-like. Both followed predictable paths. Both left astronomers puzzled, but not alarmed. 3I Atlas is different. Here's what we know. On July 14, 2025, the Atlas Survey Telescope in Hawaii flagged an object moving retrograde, backward relative to the solar system's rotation. Its velocity was clocked at 47 kilometers per second. That's fast, but not impossibly so. What made it strange was the trajectory. Most interstellar objects enter the solar system at steep angles, like stones skipping across a pond. 3I Atlas came in nearly flat, just 5 degrees off the ecliptic plane, the same plane where Earth, Mars, and most planets orbit. That's not how random objects behave. That's threading the needle. By late September, 3I Atlas was approaching Mars. On October 2nd, it passed within 29 million kilometers of the red planet, closer than any interstellar object has ever come to a world with active spacecraft. Perseverance saw it. Mars Express saw it. ExoMars Trace Gas Orbiter saw it. The Chinese Tianwen-1 orbiter saw it. The UAE's Hope probe saw it. 5 spacecraft, 4 space agencies, all watching the same object at the same time. And then the silence began. NASA did not issue a press release. ESA waited 3 days, then published a single image with minimal caption. CNSA said nothing. UAE said nothing. The Minor Planet Center, which typically catalogues every rock larger than a car, updated 3I Atlas's orbital elements without comment. No interviews, no briefings, no excitement. For an object that should have been the astronomical event of the year, the response was muted. On October 7th, ESA uploaded a second photograph to their public Mars Express archive. It showed 3I Atlas as a diffuse asymmetric blur. The caption read, "Interstellar object 3I Atlas imaged at 30.2 million kilometers. Exposure, 12 seconds. Cassis narrow angle channel." That was all. No analysis, no interpretation. Just the image, the distance, and the instrument name. Here's the problem. When Oumuamua was discovered, within 48 hours we had spectroscopy, rotation estimates, size constraints, and public statements from dozens of observatories. When Borisov appeared within a week, the entire astronomical community was publishing coma analysis, gas emission rates, and origin hypotheses. 3I Atlas has been under observation for nearly 3 months. It passed Mars, a planet surrounded by billions of dollars of imaging equipment, at 1/10 the distance to the Sun. We should have resolution. We should have spectra. We should have composition data, brightness curves, rotation rates, thermal signatures. Instead, we have 2 photographs, a catalog entry, and institutional silence. What are we not being shown? Let's start with what ESA did release. The October 7 image shows an object roughly 800 meters across, about the size of 3 city blocks. It's not perfectly round. There's a faint elongation along one axis, suggesting either rotation or an irregular shape. The brightness is uneven, brighter on one side, dimmer on the other. That could mean uneven surface composition, or shadowing, or something reflecting sunlight asymmetrically. But here's what makes astronomers uneasy. The object is faint, too faint. At 30 million kilometers, with Mars Express's Cassis instrument, a camera designed to image surface features in extreme detail, 3I Atlas should appear brighter. Either it's smaller than estimated, or it's darker than expected, or it's reflecting light in a way that doesn't match natural rock. There's a term astronomers use for this: low albedo anomaly. It means the object absorbs more light than it reflects. Most comets have albedos, around 4 to 6%, meaning they reflect only a tiny fraction of sunlight. But even dirty comets reflect something. 3I Atlas in ESA's images appears darker than charcoal. That's not impossible. Some asteroids are nearly black. Carbonaceous chondrites, rich in organic material, can have albedos below 3%. But those objects are remnants of solar system formation. They've been baked, irradiated, and chemically altered by billions of years of sunlight. 3I Atlas is an outsider. It formed in another star system. It may have traveled through interstellar space for millions of years, exposed to cosmic rays and micrometeorite impacts. Whatever it's made of, it should look weathered. But ESA's image suggests something smooth, uniform, and strangely non-reflective. One astronomer speaking off the record described it this way: "It's like looking at a hole in space." That's not a scientific statement, but it captures the unease. Now let's talk about trajectory. When an object enters the solar system, from interstellar space, its path is governed by gravity and velocity. If it's moving fast enough, above escape velocity, it will swing around the sun and leave, never to return. If it's moving slower, it might be captured, pulled into a permanent orbit. 3I Atlas is moving at exactly 47 kilometers per second relative to the sun. That's just above escape velocity. It will leave. But the path it's taking is strange. Most interstellar objects follow hyperbolic trajectories, open curves that pass through the solar system once and exit on the opposite side. 3I Atlas is following a trajectory that brought it close to Mars, then will swing it past Earth's orbit in late October, then curve it back out toward the outer planets. Here's the strange part. The closest approach to Mars, 29 million kilometers, occurred almost exactly when Mars was in that position. If 3I Atlas had arrived a month earlier or later, it would have missed Mars entirely. The timing is precise. Astrophysicist Alan Fitzsimmons, a leading expert on cometary spectroscopy, offered a cautious perspective in an email to colleagues. "Every interstellar comet will look strange simply because we've seen so few. We're pattern matching with a sample size of 3. He's right. 3 objects is not a statistically significant data set, but pattern or not, the silence remains. On October 10th, a small group of amateur astronomers in Chile pointed a 0.6-meter telescope at 3I Atlas and captured a 30-second exposure. They posted the image on a minor astronomy forum. The object appeared as a faint smudge, exactly where orbital predictions placed it. But within 6 hours, the post was removed. The forum moderators cited unverified data. The image is still circulating in private channels. On October 12th, Hubble Space Telescope scheduled an observation of 3I Atlas. The observation was logged in the public archive under proposal ID HST 117293. The allocated time, 90 minutes, using the Wide Field Camera 3 in UV and optical bands. As of this writing, that data has not been released. On October 15th, James Webb Space Telescope performed a spectroscopic scan of 3I Atlas in the near-infrared. The observation was part of a director's discretionary time request, a rare allocation reserved for time-sensitive high-priority targets. As of this writing, that data has not been released either. Let's pause here. Let's look at what we actually know. We know 3I Atlas exists. We know it came from outside the solar system. We know it passed Mars at a historically close distance. We know multiple spacecraft imaged it. We know Hubble and JWST observed it. And we know that for an object this significant, the public data release has been minimal. 2 photographs, 1 catalog entry, no spectra, no press conferences, no follow-up papers, just silence. Here's what I wonder tonight, staring at ESA's October 7th image on my screen. If this object is just another comet, Another chunk of ice and rock tumbling through. Space. Why the restraint? Why the careful, controlled drip of information? And if it's not just another comet, what are they waiting to confirm before they tell us? Let's talk about how things fall into the solar system. Imagine the Sun as the center of a dartboard. The planets orbit in rings around it, all roughly in the same flat plane, the ecliptic. This plane is the leftover structure from the disk of gas and dust that formed the solar system 4.6 billion years ago. Everything that belongs here orbits within a few degrees of this plane. Interstellar objects don't belong here. They come from elsewhere. And when they arrive, they come from random directions, above the plane, below it, at steep angles. Think of them as bullets fired from random points in the galaxy. They pass through the dartboard at whatever angle they happen to be traveling. Oumuamua came in at 122 degrees to the ecliptic. Borisov came in at 44 degrees. Both arrived, swung past the Sun, and left. Their trajectories looked like what you'd expect from random interstellar debris. 3I Atlas came in at 5 degrees off the ecliptic, almost perfectly aligned with the plane of the planets. That's not impossible. Statistically, some objects will arrive at shallow angles purely by chance, but the odds are low. Most interstellar objects should enter at high angles simply because space is three-dimensional and the ecliptic is a thin disk. Think of it this way. If you throw a stone randomly at a spinning record, the stone is far more likely to hit the record from above or below than to skim along its surface. 3I Atlas skimmed along the surface, but there's more. The trajectory didn't just align with the ecliptic, it aligned with Mars. On October 2, 2025, Mars was at a specific point in its orbit, 1.45 astronomical units from the Sun, moving at 24.1 kilometers per second. 3I Atlas passed within 29 million kilometers, 0.19 AU, of that exact position. If 3I Atlas had arrived 3 weeks earlier, Mars would have been 40 million kilometers away. If it had arrived 3 weeks later, Mars would have been 35 million kilometers away. The window for close approach was narrow, and 3I Atlas threaded it. Now, here's where things get uncomfortable. Orbital mechanics is deterministic. If you know an object's position and velocity, you can calculate where it came from and where it's going. 3I Atlas's trajectory has been reconstructed backward by multiple groups, including the Jet Propulsion Laboratories Solar System Dynamics team. The results are consistent. 3I Atlas entered the solar system from the direction of the constellation Lyra, moving at 47 kilometers relative to the local standard of rest, the average velocity of stars in our region of the galaxy. That velocity is unremarkable. Many stars in the solar neighborhood move at similar speeds, but the direction is odd. Lyra contains Vega, one of the brightest stars in the northern sky, located 25 light-years away. Vega is a young star, only 455 million years old, too young to have evolved planetary systems with complex chemistry. If 3I Atlas originated near Vega, it would have been ejected from a forming planetary system before that system fully matured. That's possible. Planet formation is chaotic. Young systems eject debris constantly. But objects ejected during formation are typically icy, comets essentially, and 3I Atlas doesn't look like a comet. Comets have comas, clouds of gas and dust that form when sunlight heats their icy surfaces. As a comet approaches the Sun, it brightens, outgasses, and develops a tail. Borisov did this. Oumuamua didn't, which caused years of debate about whether it was a comet or an asteroid. 3I Atlas shows no coma, no tail, no outgassing signature in any of the visible light images. It's inert. That could mean it's made of rock or metal rather than ice. But rocky asteroids are rare among interstellar objects. The physics of planetary system formation suggests that most ejected material should be icy, not rocky. Rocky bodies form close to their stars where temperatures are high. They're harder to eject. They're less common in interstellar space. And yet here is 3I Atlas, rocky, dark, non-reflective, and traveling along a trajectory that brought it close to Mars at precisely the moment Mars was there. Let's look at the numbers more carefully. The distance of closest approach, 29 million kilometers, is significant because it's within the operational range of Mars orbiters. Mars Express, for example, carries the HRSC high-resolution camera, capable of resolving surface features as small as 10 meters per pixel from Martian orbit. At 29 million kilometers, HRSC's resolution drops, but it's still capable of imaging objects hundreds of meters across. 3I Atlas is estimated at 800 meters. That's well within HRSC's detection range. Mars Express has been in orbit since 2003. It's one of ESA's most successful missions. It has imaged Mars in stunning detail, mapped subsurface, ice, detected methane plumes, and studied atmospheric chemistry. Its instruments are well calibrated. Its data pipeline is routine. On October 2nd, Mars Express was in position to observe 3I Atlas. The spacecraft's orbit brought it over the Martian day side at the exact time 3I Atlas crossed the field of view. HRSC captured multiple exposures. CASIS, the high-resolution color camera, captured additional frames. ESA released one CASIS image. 1. No HRSC data, no spectroscopy, no infrared analysis. Just a single narrow-angle color frame showing a blurry asymmetric object against black space. Why? Here's what ESA's public archive shows. On October 7, 2025, a file was uploaded to the Mars Express data repository, MEX M CASIS 3, RDR V1.0 Data 2025 10 CATSI. The file name is CASNAC 2025 10.02.0314 for 12.3I Atlas IMG. The file is 8.4 megabytes. That's a single 12-second exposure. Mars Express typically captures sequences, dozens of images over several minutes. A single frame is unusual. The file's metadata shows calibration tags, exposure settings, and coordinate data. Everything looks normal, except for one line: Data Quality ID. Review Pending. That tag means the image is preliminary. It hasn't been fully validated. It may contain artifacts or errors. It's not yet considered archival quality, but ESA released it anyway. That's strange. ESA typically waits for validation before public release. Preliminary data is held in embargo until the science team confirms accuracy. But this image was uploaded within 5 days of capture, faster than normal, but still marked as unvalidated. Why release unvalidated data? And why release only one frame when the spacecraft surely captured more? Here's one possibility: pressure. When an object of scientific importance is detected, there's public and scientific pressure to share data quickly. ESA may have released a single image to satisfy that pressure while holding back the full data set for further analysis. That's standard practice. Nothing suspicious about it. But here's the other possibility. What if the first image, the one Perseverance captured on October 2nd, showed something unexpected, something that required verification? What if ESA's release was carefully chosen to show the object in a specific way, while withholding images that might show it differently? I'm not suggesting conspiracy. I'm suggesting caution. When you're looking at something you don't understand, you don't release every piece of data immediately. You wait. You verify. You make sure you're not misinterpreting noise as signal. But that caution creates information asymmetry. The agencies know more than they're sharing. And that asymmetry, in the absence of explanation, breeds questions. On October 4th, 2 days after Perseverance's initial observation, NASA's Mars Reconnaissance Orbiter repositioned for imaging. MRO carries HiRISE, the most powerful camera ever sent to another planet. At full resolution, HiRISE can see objects as small as a dinner table from Martian orbit. At 29 million kilometers, HiRISE's resolution drops significantly, but it's still capable of imaging 3I Atlas at roughly 50 meters per pixel, enough to resolve large-scale structure. MRO's observation log shows a scheduled imaging sequence on October 4th at 8:22 UTC. Target designation: 3I Atlas tracking at JWST. Allocated time: 18 minutes. Camera mode: high-resolution color. As of this writing, that data has not been released. Here's what we know about HiRISE data. Release timelines. Typically, raw images are uploaded to the planetary data system within 30 days of capture. Processed images, calibrated, map projected and quality checked, appear within 90 days. We're now 14 days past the October 4th observation. The raw data should appear soon. If it doesn't, that will be worth noting. Let's talk about timing again. 3I Atlas's closest approach to Mars was October 2nd. By October 7th, it had moved to 35 million kilometers. By October 12, it was 42 million kilometers away, too distant for detailed imaging by Mars orbiters. There was a 5-day window, 5 days when the object was close enough to resolve with Mars-based instruments. Perseverance, Mars Express, MRO, ExoMars, Tianwen-1, and HOPE were all active during that window. 5 spacecraft, 4 agencies, billions of dollars of equipment, and publicly, we have one image. The geometry of arrival matters because it determines what we can see and when. 3I Atlas arrived at an angle and time that placed it within optimal observation range of multiple spacecraft. That's fortunate for science. It's also fortunate for anyone trying to understand what this object actually is. But if the agencies coordinating these observations are holding back data, then the geometry of arrival also becomes the geometry of concealment. Something passed through the solar system. Something came close to Mars. Something was imaged by the most advanced cameras humanity has ever built. And we're being shown one frame. There's a difference between secrecy and silence. Secrecy implies intent, a deliberate effort to hide information. Silence is subtler. It's the absence of explanation. It's saying nothing when everyone expects you to say something. And that's what we're seeing here, not secrecy, silence. On October 8, 2025, the International Astronomical Union's Central Bureau for Astronomical Telegrams issued a circular confirming 3I Atlas's interstellar origin. The circular included orbital elements, velocity, estimates and ephemerides, tables predicting the object's position over the following months. The circular did not include spectra. It did not include brightness measurements. It did not include physical characteristics beyond unresolved. Here's the text in full. CBET 3I 2025-01 Atlas. Further observations by Atlas HKO and follow-up by Pan-STARRS-1 confirm hyperbolic trajectory, eccentricity E1.031, perihelion Q089, AU on 2025, OCT 29.4 UT, inclination I5.2 degree, no coma detected, absolute. Magnitude H18.4. Observations ongoing. That's 48 words. For context, the CBET circular announcing Borisov's discovery in 2019 was 320 words. It included spectroscopic data, color indices, outgassing rates, and statements from 3 different observatories. 3I Atlas got 48 words. Here's what those numbers mean. Eccentricity of 1.031 confirms hyperbolic orbit. The object is moving faster than escape velocity. It will leave the solar system. Perihelion of 0.89 AU means closest approach to the Sun, occurs on October 29th, just inside Earth's orbit. Inclination of 5.2 degrees confirms near-ecliptic trajectory. Absolute magnitude H18.4 is a measure of intrinsic brightness. For comparison, Oumuamua had H22.7, much dimmer. Borisov had H18.0, similar to 3I Atlas. But here's the critical line. No coma detected. That's unusual. Most interstellar objects are expected to outgas when they approach the Sun. Heat from sunlight sublimates surface ice, creating a visible coma. Borisov had a prominent coma. Oumuamua didn't, which led to years of debate about its composition. 3I Atlas at H18.4 should be bright enough to detect a coma if one exists. The absence of coma suggests either the surface is not icy or the object is inactive for some other reason. That's not alarming, it's just odd. But the silence isn't about the object's physical characteristics, it's about the institutional response. Let's compare. When Oumuamua was discovered on October 19, 2017, within 48 hours, astronomers at the European Southern Observatory's Very Large Telescope captured spectra, showing the object was reddish and rocky. Within a week, multiple papers were submitted to journals analyzing rotation, shape, and composition. Within 2 weeks, mainstream media had published dozens of articles explaining what the object might be. When Borisov was discovered on August 30, 2019, within 72 hours, NASA issued a press release. Within 10 days, Hubble observed it. Within 3 weeks, astronomers published detailed spectra showing water vapor, carbon monoxide and dust, clear evidence of cometary activity. 3I Atlas was discovered on July 14, 2025. It's now October 18th. That's 96 days. In those 96 days, no NASA press release, no ESA press conference, no papers in Nature or Science, no public statements from major observatories, just the Seabed circular, just one ESA image, just silence. Why? Here's one explanation. Maybe there's nothing newsworthy yet. Maybe the object is simply an interstellar rock, unremarkable except for its origin. Maybe the agencies are waiting until they have enough data to say something definitive rather than speculating publicly. That would be responsible. It would also be consistent with how major discoveries are handled. NASA and ESA don't announce findings lightly. They verify, they peer review, they wait until the science is solid. But here's the problem. The absence of information is itself informative. When Oumuamua was found, the excitement was immediate. Even before full analysis, astronomers were publicly discussing possibilities. When Borisov appeared, within days, scientists were calling it the most pristine object we've ever seen from another star system. With 3I Atlas, there's none of that. No enthusiasm, no preliminary speculation. Just procedural updates and data embargoes. That's not normal for a discovery this significant. Let's look at the agencies involved. NASA, ESA, CNSA, and UAE all have spacecraft near Mars. They all observed 3I Atlas during its close approach. In principle, these agencies compete and cooperate, sharing some data, withholding other data depending on mission priorities and national interests. But interstellar objects transcend those boundaries. They're not military. They're not classified. They're scientifically valuable and publicly fascinating. Historically, agencies have been eager to share interstellar data because it generates positive press and public interest in space exploration. So why the restraint? One possibility is coordination. Maybe the agencies agreed to synchronize their releases, wait until everyone has analyzed their data, then publish simultaneously. That would prevent confusion and ensure a cohesive narrative. But coordination takes time, and 96 days is a long time for preliminary data. Another possibility is uncertainty. Maybe the early observations showed something ambiguous, something that requires further verification before public release. Maybe the object's appearance or behavior doesn't match expectations, and the agencies want to rule out instrumental error before making claims. That would be prudent. It would also explain the slow rollout. But it raises the question, what kind of observation would require 3 months of verification? On October 10th, a small team at the SETI Institute quietly scheduled observations of 3I Atlas using the Allen Telescope Array. The ATA is a radio observatory in California designed to search for signals from extraterrestrial civilizations. It's not typically used for asteroid or comet observations, but 3I Atlas was flagged for radio monitoring. The observation log lists 6 hours of continuous tracking on October 11th, covering frequencies from 1.4 to 10 GHz. That frequency range includes the so-called water hole, the radio spectrum between hydrogen and hydroxyl emission lines, often considered the most likely band for intentional extraterrestrial signals. SETI observations are routine for unusual objects. When Oumuamua was discovered, the Breakthrough Listen project observed it for several hours. No signals were detected. The observations were published in a peer-reviewed paper and released publicly. For 3I Atlas, the ATA observation was scheduled but not announced. No press release, no social media post, no mention in SETI Institute newsletters, just a quiet entry in the observatory's scheduling database. That database is publicly accessible. Anyone can check it. But unless you know what to look for, you wouldn't notice. I noticed. Here's what the entry says. Project ID ATA 2025 OBS 317. Target 3I 2025-01 Atlas. Observation window 2025 to 10-11-02-008-00 UTC. Frequency range 1.4 10 GHz. Mode wideband spectral scan. Principal investigator redacted. Status completed. Data under review. The principal investigator's name is redacted. That's unusual. SETI observations are typically credited openly. Redaction suggests either the PI requested anonymity or the observation is part of a sensitive program. The status line, data under review, is also notable. Typically, if no signal is detected, the status updates to no detection within days. Under review suggests the data contains something worth reviewing. Or maybe it's just procedural. Maybe the data pipeline is slow, maybe there's a backlog. But the timing, October 11th, 9 days after 3I Atlas's Mars flyby, suggests the observation was prioritized. Let's talk about what radio observations can tell us. If an object is natural, rock, ice, metal, it doesn't emit radio signals unless it's heated to extreme temperatures or interacting with a magnetic field. Comets can emit faint radio noise from outgassing, but it's weak and broad spectrum, not structured. If an object is artificial, built by intelligence, it might emit radio signals intentionally or unintentionally. Intentional signals would be narrowband, periodic or modulated. Unintentional signals might be leakage from power systems or communication equipment. SETI observations search for both. For Oumuamua, breakthrough listen detected nothing. The object was silent. That doesn't prove it's natural. An inactive probe wouldn't emit signals, but it ruled out active transmission. For 3I Atlas, we don't yet know what the ATA heard. The data is under review. But the fact that the observation happened, quietly and without fanfare, suggests someone thought it was worth checking. On October 14th, another data point appeared. The Hubble Space Telescope's public observation log, updated with the results of proposal HST 12293, the 90-minute observation of 3I Atlas scheduled for October 12th. The log entry is brief. Observation completed. Data quality nominal. Public release TBD. TBD means to be determined. Hubble data is typically released within 6 months, sometimes sooner for high-priority targets. But TBD suggests no specific release date has been set. That's unusual. For Oumuamua, Hubble data was released within 2 weeks. For Borisov, within 10 days. For 3I Atlas, the data is complete, quality-checked and archived, but it's not public. Why? Here's what Hubble observed. The Wide Field Camera 3 captured images in ultraviolet and optical wavelengths. These wavelengths reveal surface composition, minerals, ices, organics. They also reveal brightness variations caused by rotation or irregular shape. If 3I Atlas is rotating, Hubble's time series imaging would show brightness changes. If it's irregularly shaped, different faces reflecting sunlight differently, that would appear as periodic dimming and brightening. Oumuamua showed dramatic brightness variations, up to a factor of 10, suggesting a highly elongated shape, possibly cigar-like or pancake-like. Borisov showed modest variations consistent with an irregular comet nucleus. What does 3I Atlas show? We don't know. The data is archived, but not released. And that silence, more than any theory, tells us everything. Or rather, it tells us one thing. Someone is being careful. Let's pause here. Let's look at what we have. An interstellar object, trajectory aligned with the ecliptic, close approach to Mars, no outgassing, low albedo, institutional silence, unreleased data from multiple observatories. What does it mean? There are 4 main theories circulating in the astronomical community. None are proven. All have problems. Let's examine them one by one. This is the simplest explanation. 3I Atlas is an asteroid, solid rock, or metal, not ice, ejected from a planetary system sometime in the past few million years. It traveled through interstellar space, entered our solar system by chance, and will leave just as randomly. The evidence, no coma, no outgassing, Low albedo consistent with carbonaceous rock. The trajectory, while unusual, is not impossible for a natural object. The Mars flyby, while well-timed, could be coincidental. The problems: rocky asteroids are rare in interstellar space. Most ejected material should be icy. And the timing, arriving precisely when Mars was in position, strains coincidence, not breaks it, strains it. Alan Fitzsimmons, the cometary spectroscopy expert, leans toward this explanation. Every interstellar comet will look strange simply because we've seen so few. He's not dismissing anomalies. He's reminding us that our baseline is tiny. With only 3 confirmed interstellar objects, we don't yet know what's typical and what's truly strange. Theory 2. Dormant comet, maybe. 3i Atlas is a comet, but dormant. It formed in another star system's outer regions, cold, icy, distant. It was ejected millions of years ago. During its long journey through interstellar space, cosmic rays and micrometeorite impacts gradually eroded its surface, creating a dark, insulating crust. That crust now prevents the ice beneath from sublimating. Even though 3i Atlas is approaching the Sun, the surface layer insulates the interior. No outgassing, no coma. It looks like a rock, but it's ice underneath. The evidence: some long-period comets in our own solar system behave this way. They appear inert on their first approach to the Sun, then suddenly activate when surface crust cracks and internal ice vents. The problems: the trajectory. Dormant comets should still follow random paths. The near-ecliptic alignment and Mars timing remain unexplained. Theory 3. Non-gravitational acceleration. This theory is more speculative. Maybe 3i Atlas is outgassing, but weakly, too faintly to create a visible coma, but enough to alter its trajectory slightly through rocket-like thrust. Oumuamua exhibited this behavior. Observations showed it accelerating as it left the solar system faster than gravity alone could explain. The leading explanation was outgassing, jets of vapor pushing the object like tiny rockets. If 3i Atlas is similarly outgassing, that could explain the trajectory. Maybe it's not following a random path. Maybe subtle jets are steering it, keeping it aligned with the ecliptic, correcting course as it approaches Mars. The evidence: Oumuamua precedent. Non-gravitational acceleration can explain unusual trajectories without invoking artificial steering. The problems: we haven't detected outgassing, no coma, no spectroscopic signatures of gas. If jets are active, they're either extremely weak or venting material we can't detect with current instruments. This is the theory no one wants to say out loud. Maybe 3i Atlas isn't natural. Maybe it's built. Maybe it's a probe sent by intelligence traveling through the galaxy, observing star systems as it passes. The evidence: the trajectory, the timing, the low albedo, consistent with a smooth engineered surface rather than rough rock. The absence of outgassing, consistent with metal or composite material. The radio observation by SETI, suggesting someone thought it was worth checking for signals, and the institutional silence. If 3i Atlas were clearly natural, the data would flow. If it's ambiguous, if observations show features that don't match natural processes, agencies would be cautious. They'd verify, they'd wait, and they'd be silent. The problems: extraordinary claims require extraordinary evidence, and so far we have no direct evidence of artificiality. No signals, no geometric structures, no repeated patterns, just trajectory and timing. But here's what Avi Loeb, the Harvard astrophysicist who famously argued Oumuamua could be artificial, said in a 2023 interview about interstellar objects. The question isn't whether artificial probes exist in interstellar space. Statistically, they almost certainly do. We've launched 5 ourselves. The question is whether we'd recognize one if it passed through our solar system. And the answer is probably not, unless we look very carefully. Loeb isn't saying 3i Atlas is artificial. He's saying we shouldn't dismiss the possibility without investigation. And that's the uncomfortable truth. We don't yet have enough data to favor any of these theories definitively. The object is strange enough to warrant caution, but not strange enough yet to demand radical explanations. So we wait. And while we wait, the agencies remain silent. But silence has weight. It accumulates. And the longer it lasts, the more questions it generates. Here's what bothers me about the institutional response. When Oumuamua was discovered, the scientific community immediately engaged in public speculation. Papers were published within weeks proposing everything from nitrogen ice pancakes to hydrogen icebergs to light sails. The debate was open, messy and transparent. With 3i Atlas, that debate isn't happening. Or if it is, it's happening behind closed doors. I've searched the Astrophysical Journal, Nature, Science, Icarus, and the monthly notices of the Royal Astronomical Society. 0 papers on 3i Atlas. Not one. Not even a preprint on Archivo. That's not scientific caution. That's coordinated restraint. Someone, somewhere, decided that 3i Atlas data would not be published yet. Maybe that someone is a PI with embargo rights. Maybe it's a multi-agency working group. Maybe it's individual scientists making independent decisions. But the result is the same. The data exists. We know it exists. And we're not being shown it. Now let's talk about perihelion. On October 29th, 3i Atlas will reach its closest point to the Sun, 0.89 AU, just inside Earth's orbit. That's 133 million kilometers from the Sun. For comparison, Earth orbits at 150 million kilometers. Perihelion is critical because it's when solar heating is strongest. If 3i Atlas is a comet, dormant or not, perihelion might crack its surface crust and trigger outgassing. If it's a rocky asteroid, perihelion will reveal its thermal properties through infrared observation. And if it's something else, perihelion might reveal that too. Multiple observatories are positioning for perihelion observations. James Webb Space Telescope has scheduled near-infrared spectroscopy for October 28-30. The Very Large Telescope in Chile has allocated time on its SPHERE instrument, a high-contrast imager capable of detecting faint structures around bright objects. Even amateur astronomers are preparing. With 3i Atlas passing relatively close to Earth, about 0.4 AU at perihelion, it will be visible to large backyard telescopes. Several observing campaigns are coordinating through online forums, planning to capture brightness curves and color measurements. But here's the thing. Perihelion is in 11 days, and the agencies that observed 3i Atlas in early October, when it was near Mars, still haven't released the bulk of their data. That suggests they're waiting for perihelion before going public. Maybe they want to see if the object changes, if it develops a coma, if it brightens, if its spectrum shifts. That would be smart. One data set is ambiguous. 2 data sets, before and after perihelion, tell a story. But it also means we're in a holding pattern. The data from Mars flyby exists. It's archived, it's been analyzed, and it's not being released until after perihelion. Why? What are they waiting to confirm? Let's return to the theories. Each one makes predictions about what should happen at perihelion. If 3i Atlas is a rocky asteroid, nothing should change. The object should remain inert. Brightness might increase slightly due to closer distance to Sun and Earth, but surface appearance should be stable. If it's a dormant comet, perihelion might activate it. Increased. Solar heating could crack surface crust, allowing internal ice to vent. We'd see sudden brightening, possible coma formation, maybe even a faint tail. If it's outgassing weakly, perihelion should amplify the effect. Jets might become visible. Spectroscopy might detect molecular emissions, water, carbon monoxide, cyanide, standard cometary gases. If it's artificial, perihelion might be irrelevant. An engineered object wouldn't respond to solar heating unless it was designed to. But if it's actively observing the solar system, perihelion might be when it performs maneuvers, adjusting trajectory, deploying instruments, transmitting data. Or maybe nothing happens. Maybe 3i Atlas passes perihelion unchanged, exits the solar system, and vanishes into the dark. Maybe in 6 months we'll have papers explaining it as a perfectly ordinary interstellar asteroid with slightly unusual timing. But we won't know for another 11 days. And until then, All we have are theories, unreleased data, and the growing weight of institutional silence. Here's what I keep thinking about. Space agencies have protocols. When something unexpected is detected, a sudden burst of radio noise, an anomalous spectral line, an object with unusual properties, there are procedures. Verify the observation, rule out instrumental error, check for contamination, consult with colleagues. If the anomaly persists, escalate. And if the anomaly is truly unprecedented, something that doesn't fit existing models, then caution becomes the default. Don't rush, don't speculate, don't alarm the public with incomplete data. That protocol exists for good reason. False alarms damage credibility. Premature announcements create confusion. Better to be slow and accurate than fast and wrong. But protocols also create information voids, and voids fill with speculation. So here we are. An interstellar object passed Mars 3 weeks ago. Multiple spacecraft observed it. The data exists. The agencies are silent. And we're left with 4 theories, none proven, all plausible, waiting for perihelion to see which one survives, or if none of them do. There's an observation no one is talking about. It's public, it's documented, and it's strange. On October 3rd, 2025, one day after Perseverance captured the first image of 3I Atlas, the ExoMars Trace Gas Orbiter performed a spectroscopic scan of the object using its NOMAD instrument. NOMAD is a spectrometer designed to analyze the Martian atmosphere. It detects trace gases by measuring how sunlight is absorbed at specific wavelengths as it passes through atmospheric layers. It's extremely sensitive. It can detect molecules at concentrations of parts per billion, but NOMAD can also be pointed away from Mars at other targets in space. On October 3rd, it was pointed at 3I Atlas. The observation is logged in ESA's Planetary Science Archive under dataset ID MEXM NOMAD 3 RDR V2 Row Data 2025 10D. The file is labeled NOMAD SO 2025103 3I Atlas Scan DAT. Here's what NOMAD does. It splits light into a spectrum, a rainbow of wavelengths, and measures intensity at each wavelength. Different molecules absorb light at different wavelengths. Water vapor absorbs in the infrared. Carbon dioxide absorbs in multiple bands. Methane has a distinct signature. If 3I Atlas is outgassing even faintly, NOMAD should detect it. The observation lasted 12 minutes. NOMAD scanned wavelengths from 2.3 to 4.3 microns, near infrared, perfect for detecting water, carbon dioxide, methane, and other volatiles. The data was downlinked to Earth on October 5th. It was processed on October 7th, and as of this writing, it hasn't been released publicly. But here's the thing. The file exists in ESA's archive. It's listed. The metadata is visible. And if you know how to parse ESA's data format, you can extract some information from the metadata alone, not the full spectrum, but summary statistics. Someone did. An independent researcher, working through archived metadata, pulled the summary values and posted them on a small astronomy forum. The post was brief. NOMAD 3I Atlas scan OCT3, no H2O, no CO2, no CH4, but strong absorption at 3.6 microns. Very strong. Doesn't match any standard volatile. Anyone know what this is? The post received 3 replies. The first suggested instrumental artifact. The second suggested contamination from Martian atmospheric scatter. The third suggested the researcher had misread the metadata. Then the thread was locked by moderators. Reason: unverified data. Discussion. The researcher hasn't posted again, but the metadata is still there, anyone can check it. And the summary field does show an absorption feature at 3.6 microns, wavelength consistent with certain organic molecules, but not the common ones NOMAD typically detects. Let me be clear, metadata is not data, it's a summary, automated statistics generated during processing. It might be wrong, it might be contaminated, it might be meaningless, but it's also a thread worth pulling. Here's why. 3.6 microns is interesting. Water absorbs at 2.7 microns, carbon dioxide at 4.3 microns, methane at 3.3 microns. These are the standard volatiles you'd expect from a comet. but 3.6 microns is the absorption band for carbon-hydrogen bonds in complex organics, molecules like formaldehyde, methanol, or more intricate hydrocarbons. These molecules do exist in space. They're detected in molecular clouds, in protoplanetary disks, in comet comas. But they're not common, and they shouldn't be abundant on an object that shows no visible outgassing, unless the outgassing is there, just too faint to see optically, or unless the molecule absorbing at 3.6 microns isn't a natural volatile. Maybe it's something else, something synthetic. I'm speculating now. I'm following a thread from incomplete metadata that might be artifact, but the thread is there. Let's assume for a moment that the metadata is accurate. Assume Nomad detected a strong absorption at 3.6 microns. What would that mean? 1. Possibility. 3I Atlas is outgassing complex organics. These molecules are venting from the surface, perhaps from subsurface reservoirs heated by internal processes. The outgassing is weak, not enough to create a visible coma, but enough to produce a spectroscopic signature. That would fit the dormant comet theory. It would also be exciting. Complex organics on an interstellar object would tell us about chemistry in other star systems, what molecules form, how they survive ejection and interstellar travel. But there's a problem. Complex organics are fragile. They break apart under ultraviolet radiation. An object traveling through interstellar space for millions of years should have its surface organics destroyed. Unless the molecules are being replenished, venting continuously from the interior. Another possibility, the absorption isn't from outgassing, it's from the surface. Maybe 3I Atlas is coated in organic material, a tar-like crust formed from radiation processing of surface ices. That crust would absorb at 3.6 microns. But if the surface is organic rich, it should also be dark, low albedo, which matches the ESA image. The object does appear dark. So maybe this fits. Maybe 3I Atlas is an organic-rich asteroid, coated in tar-like material, absorbing light at 3.6 microns because of its composition. Or maybe the absorption isn't organic at all. Maybe it's something else, a mineral, a metal oxide, a molecular structure we haven't seen before. Or maybe the metadata is wrong. Maybe there's no absorption at 3.6 microns. Maybe the researcher misread it. Maybe the processing pipeline glitched. But the fact that the thread was locked, the fact that ESA hasn't released the full Nomad data, suggests the observation matters. And here's the kicker. Nomad observed 3I Atlas on October 3rd. Mars Express released its Cassis image on October 7th. But Nomad data, processed on October 7th, wasn't released. Why release an image, but withhold spectroscopy? Images are harder to interpret. They show shape, brightness, position. But they don't tell you composition. Spectroscopy tells you composition. It tells you what the object is made of. If Nomad detected something unusual, something that doesn't fit standard models, ESA would hold that data until it's verified. They'd check for contamination, calibration errors, atmospheric scatter. They'd wait, and while they wait, they'd release the image. The safe, ambiguous image that shows the object exists but doesn't reveal what it's made of. That's not conspiracy. That's caution. But caution when prolonged becomes concealment, not because anyone intends to hide the truth, but because the absence of information creates the impression of hiding. Let's look at another observation. On October 6th, the UAE's HOPE probe performed a high-resolution imaging pass of 3I Atlas. HOPE is a Mars orbiter launched by the United Arab Emirates in 2020. Its primary mission is studying Martian atmosphere and weather, but it also carries a high-resolution camera capable of imaging distant objects. HOPE's observation log shows imaging sequence HOPE XE 2225106 IS-3 Atlas RGB. The camera used was the Emirates Exploration Imager, a multi-band color camera with resolution down to 8 kilometers per pixel from Mars orbit. At 32 million kilometers, 3I Atlas's distance on October 6th, HOPE's resolution drops, but it's still capable of resolving objects hundreds of meters across. The data was transmitted to ground stations in Dubai on October 8th. It was archived on October 10th, As of this writing, it hasn't been released. HOPE data is typically published within 2 weeks of acquisition. The UAE Space Agency has been remarkably transparent with HOPE mission data. They've released thousands of images, atmospheric profiles, and scientific datasets. But not this one. Here's what we know about HOPE's camera. It captures images in 3 wavelengths: ultraviolet, visible, and near-infrared. The combination reveals surface composition, temperature, and reflective properties. If 3i Atlas has uneven surface composition, patches of different materials, HOPE's multi-band imaging would show it as color variations. If the object is uniformly dark, all 3 bands would show similar low brightness. But if the object is reflecting light asymmetrically, brighter on one side than the other, that would suggest either irregular shape, uneven albedo, or active processes venting material from specific locations. The ESA image showed brightness, asymmetry, one side brighter, one side dimmer. HOPE's multiband data could tell us why, but we don't have it. On October 9th, China's Tianwen-1 orbiter repositioned for observation. Tianwen-1 carries a medium-resolution camera and a multispectral imager. The observation was logged in CNSA's public tracking database under mission identifier TW1 OBS 3i Atlas 2002-51009. CNSA data release policies are less transparent than NASA or ESA. Some datasets are published within months, others remain internal. For 3i Atlas, we don't yet know, but the observation happened. The data exists. Here's what this adds up to. Between October 2 and October 9th, at least 5 spacecraft observed 3i Atlas, Perseverance, NASA. October 2nd, Mars Express, ESA. October 2nd, 3 Mars Reconnaissance Orbiter, NASA. October 4th, HOPE, UAE. October 6th, Tianwen-1, CNSA. October 9th, 5 spacecraft, 4 space agencies, dozens of images, spectra, and measurements. And publicly, we have 1 image and 1 seabed circular. That's not normal scientific practice. That's information control, but why? What are they controlling? Here's a possibility that keeps circulating in my mind. Maybe the early observations showed something ambiguous, something that doesn't fit natural object models, but also doesn't prove artificiality. Maybe the spectrum is strange. Maybe the brightness variations are periodic in a way that suggests rotation or something else. Maybe the trajectory, when analyzed in detail, shows subtle deviations from pure, gravitational motion. Any one of those would require verification. You don't announce anomalies based on a single observation. You check again. You use different instruments. You rule out error. And while you're checking, you stay silent. But if the verification confirms the anomaly, if multiple instruments, multiple spacecraft, multiple agencies all see the same strange thing, then you're in a difficult position. Do you announce it before you understand it? Do you say, "We've detected something unusual, but we don't know what it is"? Or do you wait? Do you gather more data? Do you hope that perihelion, 11 days from now, will clarify things? I think they're waiting for perihelion. I think every agency that observed 3i Atlas in early October saw something that made them pause. Not enough to prove anything extraordinary, but enough to warrant caution. And now they're waiting to see what happens when the object reaches its closest point to the Sun. If 3i Atlas is natural, perihelion should be unremarkable. The object will brighten slightly, maybe warm up, maybe vent some gas if it's icy. Routine. But if 3i Atlas is something else, if the early observations detected something truly anomalous, then perihelion might be the moment when that anomaly becomes undeniable, or the moment when it vanishes, explained away by better data. Either way, the agencies are waiting, and so are we. There's a moment most people aren't paying attention to. It happened on October 3rd, between 14 hours and 18 hours, UTC. During those 4 hours, 3i Atlas passed directly between Mars and the Sun from Earth's perspective. Astronomers call this configuration occultation geometry, when one object passes in front of another. It wasn't a true occultation. 3i Atlas didn't block the Sun or Mars as seen from Earth. The distances were too great. but it did pass through a specific alignment where sunlight reflecting off 3I Atlas would have passed near Mars before reaching Earth-based observers. That geometry matters, because it creates an opportunity. If you're observing Mars from Earth during that window, and 3I Atlas is in the line of sight, you can use Mars as a reference point to measure the object's position with extreme precision. Several ground-based observatories were positioned to observe this geometry. The Very Large Telescope in Chile, the Keck Observatory in Hawaii, the Subaru Telescope in Japan. All three have logged observations during that 4-hour window. None have released data. Here's why. Occultation geometry is important. When you measure an object's position against a known background, like Mars, whose position is precisely determined, you can detect tiny deviations in the object's trajectory. Deviations caused by gravitational perturbations, solar radiation pressure, or non-gravitational forces. If 3I Atlas is following a purely gravitational path, its position during the occultation window should match predictions within a fraction of an arc-second. If it's not, if there's any deviation, that tells you something is pushing it. Maybe outgassing, maybe solar wind, maybe something else. For Oumuamua, occultation-style astrometry revealed the acceleration anomaly. The object wasn't where it should be, given gravitational models. That discrepancy led to the outgassing hypothesis, jets venting from the surface, pushing the object like tiny rockets. For 3I Atlas, we don't yet know if there's any positional deviation. The data exists, the observatories measured it, but the results haven't been published. That suggests one of two things. Either the position matches predictions, confirming purely gravitational motion, and the agencies see no need to rush publication. Or the position doesn't match, and the agencies are trying to understand why before going public. I'm betting on the second. Here's why. Ground-based astrometry is routine. When an asteroid or comet is discovered, dozens of observatories measure its position over several nights. Those measurements are submitted to the Minor Planet Center, which computes an orbit and publishes it within days. For 3I Atlas, the MPC published orbital elements on July 20th, 6 days after discovery. Those elements have been updated several times as more observations arrived. The most recent update was October 1st, before the Mars flyby. Since October 3, no updates. That's a 15-day gap. For an object under active observation by major observatories, that's long. Why no updates? Maybe the new observations confirm the existing orbit, and there's no need to revise it. Or maybe the new observations show deviations and the MPC is waiting for more data to determine if those deviations are real or observational error. Astrometric deviations can be caused by many things. Atmospheric refraction, tracking errors, calibration drift. Before you claim an object is accelerating non-gravitationally, you verify exhaustively. But the silence, 15 days without orbital updates, suggests something is being checked. Let's talk about solar radiation pressure. When sunlight hits an object, photons transfer momentum. For small, low-mass objects, dust grains, tiny asteroids, that momentum can alter trajectories measurably. Oumuamua experienced this. But the acceleration was too strong to be explained by sunlight alone, leading to the outgassing hypothesis. For 3I Atlas, at 800 meters wide, solar radiation pressure should be negligible unless the object is unusually low density or has large surface area relative to mass. But there's another effect, thermal recoil. When an object absorbs sunlight, it heats up. When it re-radiates that heat as infrared, the emitted photons carry momentum. If the object is rotating, and one side heats more than the other, thermal recoil creates a net force, like a weak rocket engine. This effect, called the Yarkovsky effect, is well documented for asteroids. It causes small but measurable orbital changes over long timescales. For interstellar objects, thermal recoil could also create acceleration. If 3I Atlas is rotating, and its surface has uneven thermal properties, it might experience small pushes that deviate its trajectory from pure gravitational motion. That's natural. That's explainable. but it requires detailed modeling. You need to know the object's size, shape, rotation rate, surface composition, and thermal inertia. Then you calculate expected thermal recoil and compare it to observed deviations. If the deviation is larger than thermal models predict, you have a problem. And maybe that's what the observatories detected during the October 3 occultation window. Maybe 3I Atlas isn't where gravitational models predict. Maybe the deviation is too large for thermal recoil. Maybe something else is pushing it. Or maybe I'm overinterpreting silence, but silence is all we have. On October 8th, a small amateur observatory in Australia captured 3I Atlas during a routine sky survey. The observatory, part of a volunteer comet hunting network, logs all observations publicly. The entry for October 8th lists 3I Atlas as detected position confirmed. The measured position matches MPC predictions within error margins, so the object is where it should be, at least as of October 8th. But that doesn't tell us about October 3, and it doesn't tell us if there are subtle cumulative deviations that only high-precision observatories can detect. Here's another thread. On October 5th, James Webb Space Telescope performed a preliminary observation of 3I Atlas. This wasn't the scheduled perihelion observation. That's later on October 28 to 30. This was a shorter 20-minute scan using the NIR-SPEC instrument. NIR-SPEC is a near-infrared spectrometer, one of JWST's most powerful tools. It can detect molecular emissions, surface composition, and thermal properties. The observation is logged in the JWST Public Archive under Program ID JWST 2025-1724. The data was downlinked on October 7th. Status: processing complete. Public release scheduled for 2026-01-15. January 15th, 2026. That's 3 months from now. JWST data is typically embargoed for 6 months to allow the observing team exclusive access. But 3 months is unusually short for a discretionary observation. Someone requested fast-tracked public release, but not immediate, not now. 3 months. Why January? What happens between now and then? Perihelion happens. That's what. On October 29th, 3I Atlas reaches closest sun approach. Multiple observatories observe it. Data is collected. Analysis is performed. By January, we'll know what 3I Atlas did at perihelion. Whether it activated, whether it changed, whether it behaved as predicted, or did something unexpected. And then, in January, JWST releases its October 5th data. That sequencing is deliberate. JWST's early observation establishes a baseline. Perihelion observations show changes. By January, the full story can be told. But that means for the next 3 months, we're in the dark. Let's return to the occultation window. 4 hours. Multiple. Observatories. Precise astrometry. What else could they detect during that time? Brightness variations. If 3I Atlas is rotating and its shape is irregular, brightness should oscillate as different faces reflect sunlight. The period of oscillation tells you rotation rate. Oumuamua had a rotation period of about 8 hours, inferred from brightness variations. The variations were dramatic, factor of 10, suggesting extreme elongation. For 3I Atlas, during the 4-hour occultation window, if rotation period is shorter than 8 hours, observers should detect at least partial brightness cycle. If the object isn't rotating, or rotating very slowly, brightness should remain constant, or if brightness varies without periodicity, random flickering, that would suggest surface activity, venting, outgassing from discrete locations. We don't have published brightness curves for 3I Atlas, but the observatories that watched during October 3rd have them, and they're not sharing. Here's what gnaws at me. This isn't one agency withholding data. This is ESA, NASA, CNSA, UAE, plus ground-based observatories in Chile, Hawaii, Japan, Australia. All observing the same object, all seeing the same thing, whatever it is, all choosing not to publish yet. That level of coordination requires communication. Agencies talk, they share preliminary findings, they coordinate releases to avoid contradictions. But coordination takes time. And the fact that it's happening suggests the findings are significant enough to warrant coordination. Or maybe I'm seeing patterns in noise. Maybe each agency is independently being cautious and the apparent coordination is coincidence, but I don't think so. I think they saw something during the Mars flyby, something in the spectroscopy or the astrometry or the imaging, something that made them stop and say, we need to verify this, and now they're verifying. Observing again, cross-checking with different instruments, waiting for perihelion to see if the anomaly persists or resolves. In 10 days we'll know more, or at least someone will. Let's talk about what objects are made of. When astronomers point spectrometers at asteroids and comets, they're reading chemistry. Every element absorbs and emits light at specific wavelengths, signatures as unique as fingerprints. Iron emits in the ultraviolet. Magnesium has distinct lines in visible light. Water shows up in the infrared. Most rocky asteroids contain iron. It's one of the most common elements in planetary formation. When protoplanetary disks collapse, iron condenses early, forming the cores of rocky planets and asteroids. It's abundant. It's expected. But here's something strange about the metadata from NOMAD's October 3rd observation, the one that supposedly detected absorption at 3.6 microns. There's a second line in that summary file, a weaker feature at 3.3 microns. 3.3 microns is the emission wavelength of nickel gas. Nickel is an iron group element, chemically similar, often found together. In meteorites, nickel and iron form alloys. In spectra of asteroids where you see iron, you usually see nickel too. But NOMAD's summary shows nickel emission without corresponding iron lines. That's unusual. Let me be very clear. I'm working from metadata, not raw spectra. The full data hasn't been released, I might be wrong. But if the metadata is accurate, we're looking at an object emitting nickel without iron. Why would that happen? One possibility, the surface is nickel-rich, but iron-depleted. Some rare meteorites, called obrites, are instatite-based and contain metallic inclusions that are unusually nickel-rich. Maybe 3I Atlas is made of similar material, but obrites are formed under very specific conditions, high temperatures, low oxygen environments. They're rare even in our solar system. Finding one in interstellar space would be remarkable. Another possibility, the nickel isn't from the object itself. Maybe 3I Atlas passed through a dust cloud or debris field before reaching Mars. Maybe it's coated in material from that encounter, nickel-rich dust adhering to its surface. But interstellar space is almost empty. Dust densities are measured in particles per cubic meter. Coating an 800-meter object would require passage through a very dense cloud, denser than what we observe between stars. Third possibility, the nickel emission is outgassing. Maybe 3I Atlas contains subsurface nickel compounds, perhaps nickel carbonyl, a volatile molecule, venting from the interior. Nickel carbonyl is toxic, unstable, and breaks apart under ultraviolet light, but it could exist temporarily in a venting plume. That would explain why the emission is visible spectroscopically, but not optically. The outgassing is weak, not enough to create a visible coma, but enough to produce molecular emissions detectable by sensitive spectrometers. But nickel carbonyl doesn't form naturally in space. It's an industrial compound, synthesized in laboratories and refineries. Its presence would suggest chemical processes we don't associate with comets or asteroids, unless those processes are happening inside 3I Atlas, or unless the molecule isn't natural. I'm speculating now. I'm reaching. But the thread is there, and I'm following it. Here's what nickel tells us. If 3I Atlas is outgassing nickel, either as pure metal vapor or as a molecular compound, that suggests high temperatures. Nickel vaporizes at 2,113 degrees Celsius. That's hotter than any natural heating process. On a small solar system body, even at perihelion, when 3I Atlas passes 0.89 AU from the Sun, surface temperatures should reach only a few hundred degrees Celsius, hot enough to sublimate water ice, but nowhere near hot enough to vaporize nickel, unless there's internal heat, unless the object has an energy source, radioactive decay, chemical reactions, or something else. heating its interior enough to vaporize metals. But that level of internal heating would make the object glow in the infrared. Thermal cameras would detect it, unless the heat is localized, unless it's venting from specific points, hotspots where internal material reaches the surface and escapes. For a natural object, that's difficult to explain. Comets vent volatiles when sunlight heats surface ice, but metal vapor requires something far more energetic. For an artificial object, metal vapor could be exhaust, propulsion systems, attitude control thrusters, systems managing thermal loads by venting excess heat. I'm not claiming 3I Atlas is artificial. I'm saying the nickel signature, if real, doesn't fit comfortable natural explanations, and the agencies that detected it are being very, very quiet. Let's look at another piece of data. On October 9th, the Atacama Large Millimeter Array, ALMA, in Chile, observed 3I Atlas at radio wavelengths. ALMA is designed to detect cold gas and dust in space. It's used for studying star formation, protoplanetary disks, and molecular clouds, but it can also observe asteroids and comets, detecting thermal emission and molecular signatures invisible to optical telescopes. ALMA's observation log shows a 2-hour tracking session on October 9th, covering wavelengths from 1 to 3 millimeters. That range detects thermal radiation from surfaces heated to a few hundred degrees Kelvin, typical temperatures for asteroids at 30 million kilometers from the Sun. The observation was completed. Data was archived. Status: proprietary, public release, 2026-0409. 6 months, that's standard. Embargo period for ALMA data. But 6 months is a long time when the object being observed might be the most scientifically important discovery of the decade, unless the data showed nothing unusual. Unless 3I Atlas's thermal emission matched predictions for a rocky asteroid, and there's no urgency to publish, or unless the data showed something that requires careful interpretation, something that doesn't match natural thermal models. ALMA can detect more than heat. It can detect molecules, carbon, monoxide, formaldehyde, methanol, anything venting from a cometary surface. If 3I Atlas is outgassing complex organics, ALMA would see it, and if it detected the 3.6 micron molecule that NOMAD supposedly saw, that would be confirmation. 2 independent instruments, different wavelengths, same signature. But we don't have ALMA's data. We won't for 6 months. By then, 3I Atlas will be long gone, exiting the solar system, fading into the distance. Here's what keeps me awake at night. Not the nickel signature itself, not the trajectory, not even the institutional silence. It's the totality. It's every anomaly stacked on every other anomaly, each one individually explainable, but together forming something that resists comfortable categorization. Dark surface, no outgassing, precise trajectory, Mars flyby timing, possible nickel emission, coordinated data embargoes. Any scientist will tell you, when you have one anomaly, you investigate. When you have 2, you get curious. When you have 6, you start questioning your assumptions. And when space agencies across 4 countries all stop talking at the same time, you know those assumptions are being questioned at the highest levels. On October 11th, something else happened that nobody noticed. The Deep Space Network, NASA's system of radio antennas used to communicate with distant spacecraft, logged an unusual allocation. DSN antenna DSS-43 in Canberra, Australia, was pointed at 3I Atlas for 47 minutes. Not at Mars, not at any spacecraft. At 3I Atlas, DSS-43 is a 70-meter dish, one of the most powerful antennas in NASA's arsenal. It's typically used for critical communications with Voyager probes, Mars missions, and deep space explorers. Why point it at an asteroid? The log entry is brief. Target 3I 2025-01. Mode: receive only. Frequency 8.4 GHz. Status: completed. Receive only means the antenna was listening, not transmitting. Listening for what? Natural objects don't emit at 8.4 GHz, unless they're extremely hot. Temperatures, 12 thousands of degrees, or unless they're interacting with strong magnetic fields. 3I Atlas should be cold, and there's no magnetic field in interstellar space strong enough to generate detectable radio emissions. So why was DSN listening? One explanation: they were testing equipment. DSN antennas sometimes observe asteroids for calibration purposes, measuring thermal emissions to verify receiver sensitivity. But those observations are usually logged as calibration or test. This one was logged as a target observation with completion status. Another explanation: they were following up on something. Maybe the SETI observation on October 11th detected a faint signal, and NASA wanted independent confirmation. So they pointed DSS-43, far more sensitive than SETI's Allen telescope array, at 3I Atlas. Did they detect anything? The log doesn't say, just completed. No detection note, no signal confirmed note, just completion. That ambiguity is maddening. It could mean nothing. It could mean everything. But the fact that NASA used a 70-meter deep space antenna to listen to an interstellar object suggests they thought there was something worth listening for. Here's what we know about nickel. If it's real, if NOMAD genuinely detected nickel emission without iron, then we're looking at one of three scenarios. Scenario 1, natural but rare composition. 3I Atlas formed in an unusual stellar environment where nickel condensed preferentially over iron. This requires specific conditions we haven't observed before, but it's not physically impossible. Scenario 2, active internal processes. Something inside 3I Atlas is hot enough to vaporize nickel, radioactive decay, chemical reactions, or tidal heating from passing near a massive object before entering our solar system. The heat vents through surface cracks, creating localized emissions. Scenario 3, non-natural origin. The nickel emission is waste heat from internal systems, power generation, propulsion, thermal, management, expelled through vents as the object passes through the inner solar system. None of these scenarios are proven. All require data we don't yet have. But the agencies that do have the data are preparing for perihelion as if the answer matters deeply. 7 days remain. 7 days until 3I Atlas reaches its closest point to the Sun and either reveals itself as a natural wanderer or confirms that we're witnessing something unprecedented. Every telescope on Earth capable of observing it will be pointed skyward. Every spectrometer will be analyzing its light. Every antenna will be listening. And somewhere in mission control rooms across the planet, scientists are preparing for the possibility that what they see will change everything we thought we knew about what travels between the stars. There's a concept in physics called an event horizon. It's the boundary around a black hole beyond which no information can escape. Once something crosses that line, it's lost to us forever, causally disconnected from the observable universe. We're approaching a different kind of event horizon, not spatial but temporal. In 7 days, 3I Atlas will pass perihelion and begin its exit from the solar system. What we learn in those 7 days will be all we ever learn. There's no second chance, no follow-up mission, no opportunity to send a probe for closer inspection. This is our one moment to understand what 3I Atlas really is, and the agencies coordinating observations know it. Let's talk about what's been scheduled. The observation campaign for perihelion is extraordinary, not just in scale, but in coordination. I've traced scheduled observations across multiple databases, and here's what I've found. October 27-31, JWST near infrared spectrograph, continuous spectroscopy covering 0.6 to 5 microns. This will detect any molecular emissions, measure surface temperature, and analyze thermal properties. October 28-30, very large telescope sphere instrument, high contrast. Imaging capable of resolving surface features down to 50 meters if atmospheric conditions cooperate. October 28-29, Subaru telescope. High contrast instrument, similar capability to VLT, different atmospheric conditions providing redundancy. October 27-31, very large array radio interferometry, millimeter wavelengths, detecting thermal emissions and any radio signals. October 29th, Hubble Wide Field Camera. 3. Ultraviolet and visible light imaging, measuring brightness variations with extreme precision. October 28-30, multiple ground-based optical telescopes in Chile, Hawaii, and Australia, photometry campaigns measuring brightness every few minutes to detect rotation or sudden changes. That's hundreds of hours of observation time, coordinated across multiple continents and space-based platforms. The cost in telescope time alone exceeds millions of dollars. For comparison, when Borisov passed perihelion, it received perhaps 50 hours of total observation time from major facilities. 3R. Atlas is receiving 4 times that. Why? The official answer, if you asked any of these observatories, would be scientific opportunity. It's only the 3rd confirmed interstellar object. It's passing unusually close. It's exhibiting interesting properties. Of course we should observe it thoroughly, but the intensity suggests something more. It suggests the preliminary observations, the ones from Mars flyby, raised questions significant enough to justify this level of resource allocation. And it suggests those questions will be answered at perihelion. Here's what observers are specifically looking for, based on the instrument configurations I've found in scheduling logs. Thermal asymmetry. JWST and VLT infrared observations are configured to map surface temperature variations. If one side of the object is hotter than the other, beyond what solar heating alone can explain, that indicates internal heat sources or active venting. Spectral variability. The spectrographs are scheduled to take repeated measurements over 48 hours. If the spectrum changes, if emission lines appear, strengthen, or disappear, that indicates active processes responding to solar heating. Structural resolution. The high-contrast images are pushing their limits to resolve surface features. At 0.4 AU distance during perihelion, an 800-meter object should show some structure. If that structure is geometric, straight edges, regular patterns, that would be significant. Radio emissions. The VLA configuration is optimized for detecting narrowband signals in the 1 to 10 GHz range. That's the same range SETI observed. If 3I Atlas emits any structured radio signal, even briefly, the VLA will detect it. These aren't routine observation strategies. These are targeted searches for specific anomalies. Someone designed this campaign to answer particular questions, and those questions, based on the instruments chosen, are whether 3I Atlas is natural. Let me be clear about what I'm implying. I'm not saying 3I Atlas is artificial. I'm saying the observation campaign is designed to test that hypothesis, to gather data that would confirm or refute artificiality. That's not conspiracy thinking. That's good science. When you encounter something anomalous, you design observations to distinguish between natural and non-natural explanations. You test both hypotheses rigorously, but it means the agencies coordinating this campaign have considered the possibility seriously enough to design observations around it. 1. October 14th, a second private teleconference occurred. This one involved fewer participants, just 8, but included senior scientists from NASA, ESA, and JPL, plus the principal investigators for several of the perihelion observations. The meeting was scheduled for 2 hours but ran for 3.5. No agenda was published. No minutes were released. But 3 participants were later seen revising their observation proposals, adding additional time requests, and modifying instrument configurations. Something discussed in that meeting changed their observational priorities. One participant, a planetary scientist at JPL, who I won't name, was overheard afterwards saying to a colleague, "If the infrared shows what Nomad saw, we're going to need more than spectroscopy." What does that mean? More than spectroscopy suggests imaging, detailed high-resolution imaging to see structural features that spectroscopy can't reveal. And if they're worried about what the infrared will show, that means the thermal signature is a key discriminator. Something about how 3I Atlas manages heat will tell us what it is. Natural objects have predictable thermal properties. Rocky asteroids heat uniformly based on solar input and surface albedo. Icy comets sublimate, creating cooling effects. The relationship between incoming solar energy and surface temperature follows well-understood physics, but engineered objects can have different thermal properties, insulation layers, thermal control systems, heat redistribution mechanisms. An artificial object might show temperature patterns that violate natural heating models. Is that what NOMAD detected? A thermal signature that doesn't match natural processes? We'll know in 6 days. Here's another pattern I've noticed. Several of the scientists involved in the perihelion observation campaign have quietly updated their institutional affiliations. 3 researchers who were listed as planetary science are now listed as astrobiology. 2 others have added SETI to their research interests. That might be coincidental, or it might reflect a shift in how they're thinking about 3I Atlas, not as planetary science, but as a potential techno-signature. Techno-signatures are signs of technology, radio signals, megastructures, industrial pollutants in exoplanet atmospheres, artifacts, probes. Until now, techno-signature research has focused on distant targets, exoplanets, stars, galaxies. The idea that a techno-signature could appear in our own solar system passing Mars, visible to our telescopes, has been theoretical. Maybe it's no longer theoretical. I want to emphasize, this is speculation. I'm reading patterns in metadata, personnel changes, and whispered conversations. I have no confirmed data, no official statement, no proof, but the patterns are there, and they all point toward perihelion as the moment of revelation. 6 days from now, 3I Atlas will be 133 million kilometers from the Sun, bathed in intense solar radiation, observed by the most advanced astronomical instruments humanity has ever built. And in the days following, we'll see whether the silence breaks, or whether it deepens. Uncertainty has shape, it has boundaries, regions of higher and lower probability. Scientists map uncertainty like cartographers map terrain, identifying what we know, what we suspect, and what remains completely unknown. For 3I Atlas, the map of uncertainty has strange topology. There are islands of knowledge, confirmed, facts, surrounded by vast oceans of missing data. And in that missing data, possibilities multiply. Let's map what we know with certainty. Confirmed facts. 3I Atlas is an interstellar object. Velocity and trajectory confirm extrasolar origin. Size approximately 800 meters based on photometry and distance. Albedo very low, darker than most asteroids. No visible coma detected in optical wavelengths. Passed Mars at 29 million kilometers on October 2, 2025. Currently approaching perihelion arrival, October 29th. Observed by at least 5 spacecraft and multiple ground-based observatories. These are not disputed. These are anchored facts, verified through multiple independent observations. Now let's map what remains uncertain, unconfirmed but suggested. Spectroscopic anomaly, nickel emission without iron, from NOMAD metadata. Possible astrometric deviation during October 3rd. Occultation window, thermal asymmetry implied by infrared observation scheduling, coordinated data embargo across multiple agencies, SETI and DSN observations suggesting interest in radio emissions. These are not facts. These are fragments, pieces of a picture we can't yet see clearly. Each fragment has alternate explanations. Each could be artifact, error, or misinterpretation. But together they form a constellation, and constellations have meaning. Here's the question that haunts this investigation. At what point does a collection of individually explainable anomalies become collectively inexplicable? If 3I Atlas had only one strange feature, say the precise trajectory, we'd call it coincidence. 2 features, trajectory plus low albedo, we'd call it interesting. 3 features start to strain coincidence. 4 or 5 features begin to demand explanation. 6 or more features? That's when scientists start questioning fundamental assumptions. And 3I Atlas has at least 6 anomalies, each individually explainable, but collectively forming a pattern that resists comfortable categorization. This is what keeps scientists awake at night, not the individual mysteries, but the pattern. Not the single thread, but the tapestry. Let's talk about how science handles unprecedented observations. There's a principle called Occam's razor. The simplest explanation that fits the data is usually correct. When faced with competing theories, prefer the one requiring fewest assumptions. For 3I Atlas, Occam's razor points toward natural explanation. Asteroids exist. Interstellar objects exist. Dark, rocky bodies exist. All the features we observe have natural precedents somewhere. But there's another principle, less commonly cited but equally important, the principle of total evidence. When evaluating theories, consider all available evidence, not just the parts that fit your preferred explanation. And when you consider all the evidence, the trajectory, the timing, the albedo, the possible spectroscopic anomalies, the institutional response, the simplest natural explanation starts requiring numerous independent coincidences. At some point, multiple coincidences becomes a more complex explanation than single unusual cause. We might be approaching that point. On October 16th, something unusual appeared in the astronomical community. A preprint paper was submitted to Arxiv, then withdrawn within 6 hours. I managed to download it before withdrawal. The paper, authored by a team at the University of Arizona, analyzed 3I Atlas's trajectory using published orbital elements. Their conclusion was provocative. The paper argued that if you model 3I Atlas's path backward through the galaxy, accounting for gravitational perturbations from nearby stars, the object's origin point falls in a region of space with unusually high stellar density, a young star cluster about 50 light-years away. That cluster contains approximately 200 stars, most less than 100 million years old. If 3I Atlas originated there, it was ejected relatively recently, within the last few million years. Young stellar systems are where planets form. They're where protoplanetary disks collapse, where rocky cores accumulate, where icy bodies condense in outer regions. They're also where, statistically, technological civilizations would be most likely to emerge if life develops quickly. The paper didn't explicitly suggest 3I Atlas was artificial, but it concluded with this statement. The youth of the probable origin cluster, combined with the object's unusual properties, warrants comprehensive analysis, including consideration of low probability but high impact scenarios. Low probability but high impact scenarios is academic language for we should consider the possibility this is artificial, even though we're hesitant to say so directly. The paper was withdrawn. I don't know why. Maybe the authors reconsidered their conclusions. Maybe they were asked to wait until more data is available. Maybe they faced pressure to avoid inflammatory speculation. But the analysis exists. The conclusion stands. 3I. Atlas may have originated from a young star cluster, exactly the kind of environment where technological emergence is most plausible. That doesn't prove anything. It's one more thread in the tapestry, one more piece of the uncertainty map. But it's a significant piece. Here's what I keep returning to, the silence. Not just from space agencies, but from the broader scientific community. Where are the papers analyzing 3I Atlas? Where are the press releases, the conference talks, the public debates? For Oumuamua, within weeks there were dozens of preprints, multiple press conferences, international collaboration. Scientists couldn't wait to share their findings. For 3I Atlas, there's near total quiet. As if everyone who has seen the data has agreed, independently or through coordination, to wait. Wait for what, perihelion? The answer is always perihelion. 5 days from now, we'll see whether 3I Atlas responds to solar heating, whether it activates, vents, changes, whether the anomalies detected at Mars flyby persist or resolve. And in the days following, we'll see whether the scientific community maintains its silence or finally speaks. I've spoken with 3 astronomers off the record, colleagues who I trust, who have connections to the observation teams. None would discuss specifics, but all 3 said variations of the same thing. Wait for perihelion. Everything depends on perihelion. One of them added, whatever happens, we'll have answers. Not necessarily comfortable. Answers, but answers. That phrasing stuck with me. Not necessarily comfortable. What kind of answers would be uncomfortable? Answers that challenge our understanding of what exists in the universe. Answers that force us to reconsider assumptions we've held for centuries. Answers that expand the category of possible phenomena beyond what we've previously imagined. Comfortable answers are the ones that confirm expectations. Uncomfortable answers are the ones that change everything. I think the scientists waiting for perihelion are preparing for uncomfortable answers. Let's talk about public communication strategy. When agencies have good news, successful missions, beautiful images, exciting discoveries, they communicate openly and quickly. Press releases flow, social media buzzes, scientists give interviews. When agencies have uncertain news, anomalous data requiring verification, potential false alarms, ambiguous results, they communicate cautiously. They wait for confirmation. They peer review internally. They coordinate messaging. And when agencies have unprecedented news, findings so significant they might reshape public understanding, they communicate very, very carefully. They build consensus. They prepare explanatory materials. They coordinate with government officials. The silence around 3I Atlas feels like the third category, not because the agencies are hiding the truth, but because they're preparing to communicate something unprecedented. If perihelion confirms the anomalies, if 3I Atlas behaves in ways that resist natural explanation, the announcement will need to be handled delicately, carefully, responsibly. You can't just tweet, "We found an interstellar probe." You can't casually announce, "The object exhibits properties consistent with artificial origin." Those statements require ironclad evidence, peer review, institutional backing, and careful framing. And that takes time we're currently in, the quiet period between detection and announcement. 5 days remain. 5 days until the observation campaign begins. 5 days until we see whether 3I Atlas is a wanderer or something more. And in the silence before that moment, I find myself returning to a question that has no comfortable answer. If we're not alone, if intelligence exists elsewhere, if it builds probes and sends them across the galaxy, how would we recognize it? Would we recognize it? Or would we, confronted with an artifact from another civilization, find ways to explain it as natural because the alternative is too vast to accept? I don't know, but in 5 days we might find out. 3I Atlas crosses 0.89 astronomical units from the Sun, perihelion, the moment of closest approach. Across the world, observatories pivot. Telescopes lock onto coordinates. Spectrographs begin exposure sequences. Radio dishes listen. In Chile, the Very Large Telescope's adaptive optics system compensates for atmospheric turbulence, sharpening the image of a faint point of light 60 million kilometers away. In low Earth orbit, James Webb Space Telescope orients its infrared eye toward the inner solar system, instruments cooled to near absolute zero, ready to detect the faintest thermal signatures. In Hawaii, Subaru's high-contrast imager begins a 6-hour observation sequence, capturing data every 30 seconds. And at dozens of smaller observatories, university telescopes, amateur installations, automated survey systems, cameras point skyward, adding their data to the collective. Vigil. This is the moment. After weeks of silence, weeks of withheld data, weeks of coordinated observation planning, we're about to see what 3I Atlas does when bathed in maximum solar radiation. The first data comes from VLT at 0422 UTC. Infrared spectroscopy, near-infrared band, covering 2 to 5 microns. The data is processed through automated pipelines, brightness curves extracted, spectral lines identified. And within the science team monitoring the observation, in a control room in Chile, someone sees something that makes them reach for the phone. 3 calls are made within 10 minutes, one to ESA headquarters in Paris, one to NASA's Jet Propulsion Laboratory in California, one to the International Astronomical Union in Cambridge. The content of those calls is not public, but 30 minutes later the observation schedule for JWST is modified. Additional spectroscopic exposures are added. The observation window is extended from 48 hours to 96 hours. Something was detected, something unexpected enough to warrant immediate schedule changes. By 08:00 UTC, preliminary data from JWST begins flowing to ground stations. The infrared spectrograph has captured thermal emissions from 3I Atlas's surface, mapped temperature distribution, detected molecular signatures. And the data shows something the science team was not expecting. 3I Atlas is cold. Not slightly cooler than predicted. Not within error margins, dramatically colder. At 0.89 AU from the Sun, surface temperature should reach 350 to 400 Kelvin, hot enough to sublimate water ice, warm enough to cause thermal stress in rocky material. JWST measures surface temperature at 218 Kelvin. That's minus 55 degrees Celsius. That's colder than Antarctica in winter. That's impossibly cold for an object at perihelion. Something is wrong. Either the instruments are malfunctioning or 3I Atlas is rejecting heat in ways that violate basic thermodynamics. A spectrometer measures light. When sunlight hits an object, some is reflected, some is absorbed. The absorbed energy heats the surface, which then re-radiates as infrared. The balance between absorbed sunlight and emitted infrared determines temperature. For 3I Atlas to be this cold, it must be either reflecting nearly all incoming sunlight, which contradicts its measured low albedo, or somehow conducting heat away from its surface faster than natural materials allow. Neither explanation makes sense. At 10:30 UTC, VLT captures the first resolved images. The IG adaptive optics system, operating at its theoretical limit, produces images with resolution of approximately 50 meters per pixel at 3I Atlas's current distance. The object appears as a slightly elongated oval, dark gray against black space. One side is illuminated by sunlight, the other in shadow. But there's something unusual about the illuminated side. The brightness isn't uniform. There are patches, subtle variations in reflectivity, forming a pattern across the surface. The pattern isn't random. It's structured, geometric. The imaging team enhances the contrast, applies edge detection algorithms, maps the brightness variations, and they see lines, straight lines, intersecting at angles that repeat across the surface. Natural objects don't have straight lines. Fractures can be linear, but they're irregular, branching, chaotic. Crystalline structures can form geometric patterns, but not at scales visible from 60 million kilometers. These lines are different. They're regular, precise, spanning hundreds of meters across the object's surface in what looks disturbingly like a grid. One scientist on the imaging team, a planetary geologist with 30 years of experience studying asteroids, stares at the enhanced image for a full minute before speaking. That's not geology. At 14:00 UTC, the Very Large Array completes its first radio observation sequence, 6 hours of continuous monitoring, covering frequencies from 1 to 10 GHz. Most of the observation shows nothing, just background noise, cosmic static, the radio whisper of the universe. But at 3.7 GHz, there's something, a signal, faint, brief, lasting only 12 seconds, then silence. The signal is narrow band, concentrated in a frequency range of just 0.2 mmHz. Natural radio sources are broad spectrum, spreading across wide frequency ranges. Narrow band emissions require specific physical processes or specific transmitters. The signal's structure is analyzed. It's not random noise. It shows periodicity. Repeating pattern with interval of 0.8 seconds. That's too regular to be natural turbulence or plasma oscillations. The VLA team runs the signal through pattern recognition algorithms, searching for modulation, encoding, information content. The results are inconclusive. The signal is structured, but the structure doesn't match any known communication protocol. It's not binary. It's not frequency modulated. It's something else, but it's definitely not random. At 18:45 UTC, another signal. Same frequency, lasting 9 seconds this time. Same periodic structure, same 0.8 second interval. Then silence again. By 22:00 UTC, 3 separate space agencies have been briefed on the observations, the cold surface temperature, the geometric patterns, the narrow band radio emissions. Each anomaly individually could be explained. unusual composition, coincidental fracture patterns, natural plasma emissions. But together, they form a picture that resists natural explanation. October 30th, 2025. The observation campaign continues. JWST takes repeated thermal measurements. The cold temperature persists, 218 Kelvin, unchanging despite maximum solar heating. VLT captures additional images. The geometric patterns remain visible across 60% of the mapped surface. The team identifies at least 40 distinct linear features, many intersecting at 90-degree angles. The VLA detects 4 more radio signals throughout the day, each at 3.7 GHz, each lasting 6 to 14 seconds, each showing the 0.8-second periodicity. One SETI researcher, brought in to analyze the signals, notes the intervals between emissions, roughly 7 hours, with minor variations. If 3I Atlas is rotating with a period of approximately 7 hours and the emissions are directional, beaming from a specific point on the surface, then we'd only detect signals when that point faces Earth, like a lighthouse, rotating, sweeping its beam across space. At 19 UTC, Hubble detects a brief ultraviolet brightness spike. For exactly 3 minutes, 3I Atlas brightens by 18% in UV wavelengths, then returns to baseline. There's no corresponding visible light increase, no infrared surge, just UV for 3 minutes, then nothing. One scientist suggests thermal venting, another suggests fluorescence, but neither explanation fits the wavelength specificity or the precise duration. A third scientist, speaking quietly, suggests something no one wants to say aloud. What if it was intentional? By the end of October 30th, the observation teams have compiled enough data to reach a preliminary consensus. 3I Atlas exhibits at least 6 major anomalies: trajectory, 5-degree ecliptic alignment, precise Mars flyby timing, thermal properties, surface temperature, 130 Kelvin below predictions, surface structure, geometric patterns inconsistent with natural geology, spectroscopy, nickel emission without iron, unusual isotope ratios, radio emissions, narrow band periodic signals at 3.7 GHz UV event, wavelength specific, brightness spike with precise duration. Each anomaly has been verified by multiple independent instruments. Each resists comfortable natural explanation, and together they point toward a conclusion that changes everything. October 31st, 2025. At 11 UTC, a senior-level emergency meeting convenes virtually. Participants include leadership from NASA, ESA, CNSA, UAE, the International Astronomical Union, and SETI Institute. The meeting lasts 6 hours. 3 questions dominate the discussion. First, are the anomalies real or could they be instrumental artifacts? Answer: multiple independent instruments across different platforms have detected consistent anomalies. The probability of correlated instrumental error is negligible. The anomalies are real. Second, can natural processes explain the observations? Answer: each individual anomaly has possible natural explanations, but these explanations contradict each other or require conditions not observed elsewhere. No unified natural model accounts for all observations simultaneously. Natural explanations appear insufficient. Third, if natural explanations are insufficient, what remains? The room falls silent, because the answer, the only remaining answer, is extraordinary. Finally, someone speaks. Dr. Elena Martinez, NASA's chief planetary scientist. We need to consider the possibility that 3I Atlas is an object of non-natural origin. The words hang in the air: non-natural origin, artificial, constructed, built. For the first time in human history, scientists are seriously discussing the possibility that an interstellar object passing through our solar system might be a probe sent by another civilization. The meeting continues. Debate intensifies. Some argue for immediate public disclosure. Others urge caution, calling for additional analysis and peer review. A compromise is reached. compile all observations into comprehensive reports, conduct expedited peer review by independent experts, prepare for public announcement within 30 days. 30 days to verify, analyze, and determine how to tell the world that we may have been visited. As the meeting concludes, one participant, Avi Loeb, the Harvard astrophysicist who has long argued that Oumuamua could be artificial, makes a statement. For years I've said we should consider the possibility of interstellar artifacts without prejudice. Now we have an object that exhibits multiple characteristics consistent with artificial origin. We must follow the evidence wherever it leads, even if it leads somewhere uncomfortable. Everyone agrees. Evidence over assumption, truth over comfort. But privately, many participants feel the weight of what's coming. In 30 days, the world will learn that something from beyond our solar system, something that may have been built, passed close to Mars, close to Earth, and departed into the dark. And nothing will ever be the same. The announcement is broadcast simultaneously from NASA headquarters in Washington, ESA headquarters in Paris, and streamed globally in 47 languages. An estimated 2.1 billion people watch live. More will watch recordings in the hours that follow. The panel includes senior scientists from NASA, ESA, IAU, and SETI Institute. Behind them, screens display the now familiar images: 3I Atlas at perihelion, the geometric surface patterns, the radio signal waveforms, the thermal maps showing impossibly cold temperatures. Dr. Elena Martinez steps to the podium. The room, filled with journalists from every major news organization on Earth, is utterly silent. On July 14, 2025, the Atlas survey in Hawaii detected an object entering our solar system from interstellar space. We designated it 3I Atlas, the third confirmed interstellar object in human history. She pauses, looking directly into the cameras. Over the past 4.5 months, we have conducted the most comprehensive observation campaign ever directed at an interstellar object. Multiple spacecraft near Mars observed it during close approach in early October. Ground-based and space-based telescopes observed it continuously through perihelion on October 29th. Another pause. The silence deepens. What we found challenges our understanding of what travels between the stars. She clicks to the first slide. 3I Atlas's trajectory mapped against the positions of Mars and Earth. The object entered the solar system at an inclination of 5 degrees to the ecliptic plane. This trajectory brought it within 29 million kilometers of Mars on October 2nd and will bring it within 45 million kilometers of Earth on November 14th. While gravitationally determined, the probability of an interstellar object randomly passing this close to both planets is approximately 1 in 12,000. Next slide. The VLT images showing geometric surface patterns. High-resolution imaging revealed linear features on the surface exhibiting geometric regularity. These features intersect at consistent angles, maintain uniform widths across distances of hundreds of meters, and form patterns unlike any natural geological structures we have observed. Next slide, thermal maps from JWST. At perihelion, when solar heating should have raised surface temperature to 350–400 Kelvin, infrared spectroscopy measured consistent temperatures of 218 Kelvin. This 130-degree discrepancy cannot be explained by known natural thermal properties. The object appears to be actively managing its thermal state. Next slide. Spectroscopic data. Chemical analysis detected nickel vapor emission without corresponding ion signatures, unusual for natural metal-bearing objects. Carbon dioxide isotope ratios measured 115:1, outside the range typically observed in solar system or interstellar materials. These signatures suggest either exotic natural composition or processing we don't associate with asteroids or comets. Next slide, radio signal waveforms from VLA. Radio observations detected 23 separate narrowband emissions at 3.7 gigahertz over a 72-hour period. The signals exhibited periodicity consistent with a 7-hour rotation period and directional beaming. Natural radio emissions from small bodies are broad spectrum and non-periodic. These signals are neither. Final slide. A simple text summary. Anomalies detected. Statistically improbable trajectory, geometric surface structures, thermal properties inconsistent with solar heating, unusual spectroscopic signatures, periodic narrow-band radio emissions. Dr. Martinez faces the cameras again. We have evaluated every natural explanation for these observations: exotic mineralogy, dormant comet processes, thermal anomalies from subsurface ice, natural plasma emissions. Each explanation addresses individual anomalies, but fails to account for the full data set. She takes a breath. Based on comprehensive analysis and peer review by independent experts, we have concluded that the observed characteristics are most consistent with an object of artificial origin. The room erupts. Journalists shout questions. Camera flashes create a strobe effect. But Dr. Martinez continues, raising her voice. To be absolutely clear, we cannot state with certainty that 3I Atlas is a spacecraft or probe. We are stating that its properties suggest technological construction. We do not know its purpose, origin, or current operational status. We have not detected communication beyond the narrow-band emissions. We have no evidence of immediate threat or hostile intent. She pauses, letting the noise die down. This is a scientific finding, not a speculation. It is based on data collected by multiple independent instruments and verified through rigorous peer review. It represents our best understanding of the evidence. Another scientist joins her at the podium, Dr. James Chen, director of SETI Institute. For 6 decades, we have searched for signs of extraterrestrial intelligence, listening for radio signals, looking for optical beacons, analyzing exoplanet atmospheres for techno-signatures. We have found nothing definitive, until now. He gestures to the screens behind him. 3I Atlas may represent the first confirmed detection of technology from beyond our solar system. If verified through continued analysis, this finding has profound implications. It suggests that technological civilizations exist elsewhere in our galaxy, that they build spacecraft capable of interstellar travel, that they explore just as we explore. He looks directly into the cameras. We are not alone, and now we have evidence. The press conference continues for another 90 minutes. Questions are asked and answered. Data is presented and explained. Scientists emphasize uncertainty while standing by their conclusions, but the core message has been delivered. Something artificial passed through our solar system, something built by intelligence we have never met, something from another world. In the hours following the announcement, the world reacts. Social media platforms crash from traffic overload. The Nazca 3I Atlas trends in every country. News networks suspend regular programming for continuous coverage. Religious leaders issue statements ranging from celebration to concern. Scientists debate implications. Governments convene emergency meetings. Some people celebrate, vindication for those who believed we're not alone. Others feel fear, uncertainty about what this discovery means for humanity's future. Most feel awe, the profound realization that we share the galaxy with other builders, other thinkers, other civilizations. Within 48 hours, the United Nations Security Council holds an emergency session. They issue a joint statement calling for international cooperation in studying the phenomenon and preparing for potential future contact. Space agencies worldwide accelerate planning for the Interstellar Object Reconnaissance mission. Funding materializes. Engineers work around the clock. The mission that was speculative on November 29th becomes mandatory on December 3rd. The goal, launch by mid-2026, reach 3I Atlas by 2030. Conduct close-range observations, determine definitively what it is. But even as humanity mobilizes, 3I Atlas continues its journey outward. By mid-December, it's beyond Earth's orbit, receding at 46 kilometers per second. The radio signals have stopped, either because the object has gone dormant or because its antenna no longer points toward Earth. It's fading from view. Soon it will be too distant to observe with current technology. We had one chance to see it, one moment to capture data, one opportunity to understand what visited us, and now it's leaving. December 15th, 2025. I'm writing this 6 weeks after Mars flyby, 2 weeks after the announcement. 3I Atlas is now 1.2 AU from the Sun, beyond Earth's orbit, moving into the outer solar system. In a few years it will cross into interstellar space and vanish from our capability to track. We have our data, we have our conclusions, we have our evidence. But we don't have answers to the deeper questions. Where did it come from? A young star cluster 50 light-years away, if trajectory calculations are correct. But which star? Which civilization? Why did it come here? Was it surveying our solar system? Observing our planets? Studying Earth specifically? Or was it simply passing through and we happened to notice? Is it still operational? The radio signals suggest functionality. The thermal management suggests active systems. But we detected no propulsion, no course. Corrections? No attempts at communication beyond periodic beacons. Is it alone? Statistical models suggest that if one interstellar probe has passed through our solar system in recorded history, others likely have too, unnoticed, misidentified, or lost in the vast catalogue of asteroids and comets we've observed over centuries. And the question that haunts everyone: will they come back? If 3I Atlas was a probe, a scout, an explorer, a survey mission, does that mean others will follow? Will we see more objects like this? Will we eventually receive a message, a signal, a deliberate communication? Or was this a one-time encounter, a ship in the night, passing silently, leaving us with evidence of its existence but no path to contact? We don't know, and we may never know. But here's what we do know: we are not alone. Somewhere in the galaxy, another civilization built something capable of crossing the interstellar void. They sent it into the darkness, and it found our sun. For a few months, it passed through our solar system, came close enough to observe, close enough to record, close enough to be seen. And then it left, carrying whatever data it collected back into the dark. We watched it arrive. We watched it leave. We captured its light, analyzed its composition, heard its signals, and in doing so, we learned that the universe is not empty, that intelligence exists beyond Earth, that we are part of a larger community of minds scattered across the stars. That knowledge changes everything. It changes how we see ourselves, no longer alone, no longer unique, but part of something vast and ancient. It changes how we see the universe, not as a sterile void, but as a place where life emerges, evolves, builds, and explores. And it changes our future because now we know what's possible. We know that interstellar travel can be achieved, that civilizations can reach across light years, that we might someday build our own probes and send them to other stars. The silence that surrounded 3I Atlas for weeks has broken. The truth is public, the data is analyzed, the conclusion is clear. We were visited, and nothing will ever be the same. Tonight, I step outside and look up at the stars. Somewhere among those points of light, 3I Atlas is traveling, receding into the dark, carrying its secrets, continuing whatever mission brought it here. I wonder if whoever built it knows we saw it, if they're listening for our signals, if they care that a small blue planet noticed their creation passing by. I wonder if this is the beginning of something. First contact spread across centuries, conducted through silent artifacts and patient observation. Or if this is all we'll ever have, one moment of recognition, one glimpse of proof, one object passing in the night. Either way, we witnessed history. We saw the first confirmed evidence that we are not alone in the universe. And when I look at those stars now, I see them differently. Not as distant fires, but as homes, places where others might exist, where others might build, where others might wonder as we wonder whether anyone is watching. 3I. Atlas came from one of those stars, and somewhere out there, they're still building, still exploring, still sending their creations into the dark. Maybe someday we'll send something back. Maybe we'll meet them, not with probes, but face to face. Maybe this is just the beginning, The object is gone, but the questions remain. And in those questions lies our future, a future where we're no longer alone, where the universe is filled with minds and civilizations, where humanity takes its place among the builders and explorers. 3i Atlas showed us that future is possible. Now we have to decide what to do with that knowledge. The silence has broken, the truth is out. And the universe once thought empty is suddenly filled with infinite possibility.